Poisson probability distribution and the corresponding discrete random variable are shown in this example. It is a distribution that is defined with this formula. As you can see, the probability that number of occurrence in the Poisson distribution happen to be equal to k times in a, let's say, interval of interest would be lambda, which is the average or mean number of occurrence in that interval of interest to the power k, and then times e to the negative lambda divided by k factorial. So this problem tries to investigate for a given Poisson problem, what are the likelihood of different things happening in part A, B, C, D, E, F. Now, just to visualize it, this probability density distribution function f of k, which is also a function of lambda. Lambda is the average number of occurrences, a parameter of the distribution. You can see that it is illustrated in this drawing or plotting of the PDF or probability distribution. On the x-axis we have k, number of occurrences that we are interested in the given interval of interest, and p of x equal to k for the probability of or likelihood of that number of occurrence happens. For different value of parameter in terms of lambda equal to 1, lambda equal to 4, or lambda equal to 10, you can see that the shape of distribution changes. As lambda is increasing, or basically the average number of occurrence per given interval of interest is increasing from 1 to 4 to 10, then the distribution is sort of converging toward more of a shape of a normal or bell-shaped distribution. Okay, so with that visualization in mind, just keep in mind that this distribution is only defined for discrete random variable on x-axis discrete values, and the connection of dots on these drawing is just for visualization. Now, going back to the problem, part A. Assuming that we are talking about a mean of 2 occurrences, so that means lambda equal to 2 in the interval of interest per time period. Okay, write the appropriate Poisson probability function. Okay, so look at the formula written on top, f of x, or you can write it if you want this way, it's all right. So in this case, we are saying f of x instead of k, and of course the function the PDF is a function of lambda equal to 2, so we will have basically the probability that, let's say, x equal to whatever x value you have is 2 to the x, lambda is 2, e to the negative 2, and then divide by x factorial. Of course, it's fine if you just say x equal to k, so 2 to the k, e to the negative 2 divided by k factorial. Doesn't matter, just the name. Okay, so that's the formula. And it is not shown in this drawing because these drawings for lambda equal to 1, 4, 10, not 2, but it is something between 1 and 4. What is the expected number of occurrences in 3 time period? Okay, that's easy. Well, we are saying the mean number of occurrence in 1 time period is 2. So we have therefore 3 times 2, 6 is the expected number of occurrences in 3 time period. Okay, write the appropriate Poisson probability function to determine the probability. So let me just make this easier to see. Okay, so what is this one? So write the appropriate Poisson probability function to determine the probability of x occurrence in 3 times period. So now we are changing our window of observation from 1 time period to 3 time period. That's super important to notice early on. In Poisson distribution, it's important to be very careful about the window of observation. In this case, we are saying 3 time period. In 3 time period, it means now the new lambda is 6, as we found in part B. Is not anymore 2, because our window of interest or observation is 3 time period, where time period is the original time period. So therefore, it would be exactly as before, meaning it is still lambda to the x, e to the minus lambda divided by x factorial. But now lambda is 6, so formula becomes 6 to the x, e to the negative 6, divided by x factorial. Okay. Part D, compute the probability of 2 occurrences in 1 time period. Round the answers to 4 decimal places. Okay, So we are saying now the window of interest for observation is 1 time period. So we are back into part A. So, but we are investigating two occurrences. So what we are trying to find is what is the probability that x is, or random variable, is equal to value 2. Okay, fine. So we're going to use the formula we found in part A, because that's for 1 time period. So it's going to be 2 to the 2, e to the negative 2. So I'm just substituting x with 2, divide by 2 factorial. Okay, if you try this in calculator, you roughly find it to be equal to 0.27 and then 0.67-ish. And then when you round it up, because you just need to keep 4 digits, then it becomes 0.2707. That's the final answer. Okay, so part E. For part E, the question is compute the probability of 6 occurrences in 3 time periods. So now we are going back to part C, because we are changing our window of interest or observation to 3 time periods. All right, and be careful about this. So in this scenario, you're saying, all right, what is the probability that x is equal to 6? And we have to use the formula we found in part C. So okay, so now we are substituting x with 6. So 6 to the 6, e to the negative 6, divide by 6 factorial. And if you compute this, you end up with 0.160623. And because we are only interested in keeping 4 decimal places, you can again approximate these to 0.1606 roughly. Okay, so that's the answer. And we are keeping 4 decimal places. Compute for part F, the last part, compute the probability of 5 occurrences in 2 time periods. So now we are changing our observation to 2 time period. We need to be careful about that. So it's a new, again, window of observation. And to do that, so we say lambda is 2 times 2, because 2 was for average or mean number of occurrences in 1 time period, but now we're interested in 2 time periods, so it's 4 number of occurrences on average in 2 time periods. So the formula for Poisson becomes this time. So remember we are talking about the lambda to the power x, e to the negative lambda, and then divide by x factorial. So our lambda is 4, so 4 to the x, e to the negative 4, divide by, okay, so let me shift it up. Okay, so what I wrote is lambda is 2 times 2, 4, and then f of x is lambda to the x, e to the negative lambda, divided by x factorial. That's the general formula for Poisson probability distribution function. And then lambda is 4, 4 to the x, e to the negative 4, divided by 4 factorial. Okay, you can compute this, and again, if you approximate to keeping 4 decimal places, you end up with about 0.563. Okay, so these are just highlighting the fact that you need to be careful about application of Poisson, which is a discrete probability distribution for discrete random variable. You're basically assuming x is Poisson distributed, then in terms of number of occurrence, then we need to have average number of occurrence for a specific window of interest, and then use that in the Poisson distribution highlighted or illustrated in these drawings to find the associated probability.